Tennis is one of the greatest sports of all time. The feeling that you get when you hit the perfect shot is inexpressible. It takes hard work and countless hours of dedication to perfect these shots, and with that comes the inevitable chore of picking up all of the balls that are scattered across the court. All tennis players and instructors know the painstaking effort that goes into picking up these balls. That's why we invented BallBot, the world's finest autonomous ballboy. Using advanced computer vision techniques, BallBot autonomously picks up tennis balls so that you can relax and enjoy your serving practice. Its state-of-the-art navigation algorithms allows it to move effortlessly on hard surface tennis courts. You can let BallBot run by simply placing it on a tennis court and by pressing start. It collects balls as you serve them, so you will never run out of balls to serve. Robust to hits from serves, it collects balls as fast as you can serve them. BallBot was designed with your convenience in mind. The removable basket can hold up to 30 balls. The battery takes less than 60 minutes to fully charge and lasts several practice sessions. So instead of picking up balls, you can relax, hydrate, and improve your techniques.
We designed several prototypes for BallBot and performed several tests before coming up with the perfect autonomous ballboy. With our algorithm and advanced computer vision, we make tennis convenient for players at all levels.
Let's talk about how BallBot was made. The hole on top of BallBot's model is where we placed a touchscreen that the user can use to turn BallBot on and off. Underneath the touchscreen is where most of BallBot's hardware lies. The main hardware is the NVIDIA Jetson Nano, which reads in data from the Intel RealSense depth camera, runs the image processing pipeline, and also performs the computer vision. It also controls the motors at the front of the robot, as well as the iRobot Create 2 base. The rechargeable LiPo battery powers the hardware in the robot and can last for about 2 hours. This battery supplies 12 volts to the motors up front, but only 5 volts to the Jetson Nano and the motor controller through the buck converter. Up front is the system to handle collecting tennis balls. This includes the arms to funnel the balls, the motors and wheels to propel the balls, and the ramp to send the ball to the basket. First, the Intel RealSense depth camera looks for tennis balls on the tennis court, and our computer vision algorithm directs BallBot towards the closest tennis ball. This tennis ball gets funneled towards the center of the robot by the 2 wooden arms. Then the balls touch either of the 2 rubber wheels that are both spinning towards the center of the robot. These wheels propel the ball up the ramp, over the robot, and into the basket behind. BallBot is constructed on top of an iRobot Create 2 base. The Jetson Nano sends signals to the base from the computer vision algorithm, which tell the robot base which direction to move in. BallBot uses computer vision to detect tennis balls and move towards them. Once balls are in frame, it uses the Intel RealSense depth camera to capture images. These images look like the ones on the top left of the screen. After reading these images, BallBot converts them to the HSV color space because this color space is better for computer vision and image processing. HSV color images look like the ones at the top right. Then we perform the color thresholding on this image in each of the 3 color channels: hue, saturation, and brightness. These thresholds look like the ones at the bottom right. Once we have these thresholds, we get a binary image such as the one at the bottom left. This image gives us pixels which we think are the color of the tennis ball and those that we think are not. We then perform noise filtering using OpenCV's erode and dilate function, which gets rid of many of the small pixels of noise that we read in. After this, we get a pretty clear image of what should and shouldn't be tennis balls. Finally, we find contours in this image which represent shapes that we think would look like a tennis ball. And if the area of these shapes is not too large or too small, we classify them as a tennis ball. Once we have these shapes, we find the center of the shape and mark it as the position of the tennis ball. You can see these marks in the top left of the screen as green targets. As we move the tennis ball across the frame, it's tracked in real time and is able to successfully track all tennis balls no matter where they are in the screen. BallBot consists of 2 major systems, the software ball tracking system and the hardware tennis ball transport system. The user interacts with the interactive GUI displayed on the touchscreen on top of BallBot. They can turn BallBot on and off with a single touch. The entire software system runs on the NVIDIA Jetson Nano. The main part of the software is the ball tracking algorithm. This algorithm takes in as input image frames from the Intel RealSense depth camera, using the Pi RealSense library. These frames go through the CV pipeline described earlier with the help of the OpenCV library. Once the position of the tennis balls are determined in the image, we locate the closest one based on the size of the balls. The position of this tennis ball is sent to the iRobot control system, which determines which direction BallBot needs to move to collect the ball. How far from the center of the image the tennis ball is determines which direction BallBot needs to turn. We use the PyCreate2 library to send the iRobot Create2-based commands over UART, describing which way to turn. The tennis ball launch control system also uses the closeness of the tennis ball to determine how fast to spin the motors. If the ball is close, we want to spin the motors so that it can be collected. However, if no balls are close, we can save power by turning off the motors temporarily. As described earlier, the ball transport system consists of tennis balls getting funneled into the robot by the wooden arms, launched up the ramp by the T81 rubber wheels, transported over the runway and into the basket at the back. The DC motors, along with the NVIDIA Jetson Nano and other hardware, is powered by the 12-volt LiPo battery. The Jetson Nano only requires 5 volts, which is supplied by the buck converter connected to the battery. Our BallBot UI is displayed on a touchscreen at the top of the robot and allows the user to easily control BallBot. The UI was integrated into the existing software using multi-threading so that user input could be listened for even when the rest of the software is running. There are 3 simple buttons in the UI, one to start collecting balls, one to stop collecting balls, and one to completely shut BallBot down. The current battery level is also displayed in the top right.
Now we'll talk about metrics, testing, and verification. We design these metrics to measure BallBot's performance and user friendliness. Our first metric measures BallBot's ability to quickly collect tennis balls. To measure this, we scattered 22 tennis balls and recorded the time it took BallBot to clean the court. We were aiming for an average pickup rate of 6 balls per minute. In actuality, BallBot was able to collect 10 balls per minute. The next metric is about BallBot's battery life. We wanted BallBot to last an entire serving practice session, which we estimated to be 30 minutes. The results from our battery life test show that BallBot's battery typically lasts about 2 hours. Our next metric focuses on user friendliness. Since BallBot will be carried on and off the tennis courts by the user, we wanted BallBot to be light and portable. During development, we aimed to keep BallBot under 20 pounds. The final version of BallBot weighs around 15 pounds, which is less than our maximum allowable weight by 5 pounds. To keep BallBot running smoothly, it needs to have a fast image processing pipeline with high throughput. The throughput measures the number of images BallBot processes per second. If the throughput is too low, BallBot will appear sluggish and performance will suffer. During design, we aim to achieve a throughput of 10 images per second. Our test showed that our image processing pipeline is able to process 30 images per second. Our next 2 metrics concern the direct performance of BallBot. We wanted BallBot to rarely see non-existent tennis balls, as phantom tennis balls would distract BallBot and lower its efficiency. In the world of binary classification, detecting a tennis ball when there is not one present is called a false positive. We shot for a false positive rate of less than 5%. During our tests, we achieved a 1% false positive rate under consistent lighting conditions. This rate, however, worsened to 10% when the lighting was inconsistent. We also don't want BallBot to miss an existing tennis ball. This kind of error is called a false negative. We strove to achieve a false negative rate of less than 5%. Our tests revealed that BallBot had a false negative rate of less than 1%. Our final metric measures the consistency of BallBot. We wanted BallBot to consistently launch tennis balls with sufficient velocity so they land in its basket. During testing, we found that BallBot never missed its basket. While developing BallBot, we considered numerous approaches, some of which we had to abandon. For the design of our basket, we were forced to make it shallow and wide to meet our ball capacity requirement. This in turn made it harder for BallBot to turn/maneuver. We also loosened the thresholds in our ball detection algorithm to make it more robust to lighting changes. However, this slight modification increased our false positive rate. Finally, for material, we were originally going to use acrylic for BallBot's frame, but we eventually settled on wood for its greater material strength. This had the trade-off of increasing the overall weight of BallBot and lowering our resistance to weather. Our dream is to make tennis more efficient and to help players improve their shots. We are very excited about BallBot, and we can't wait to bring the future of tennis to your tennis courts.